In this problem, an amusement park ride consists of a large vertical cylinder that spins about its axis fast enough such that any person inside is held up against the wall when the floor drops away, as you can see in this figure in here. The coefficient of static friction between the person and the wall is given by μs, and the radius of the cylinder is r, capital R. Now you have to show that the maximum period of revolution that is necessary to keep the person from falling is given by this expression. So T is equal to square root of 4 pi squared r mu s divided by G. And then in part B, you have to obtain a numerical value for this period when r is equal to 4 meters and mu s is equal to 0.4. And in this case, you have to calculate how many revolutions per minute does the cylinder make. So let's start by just explaining again what is the problem. So you have in an amusement park, this is one of these amusement park ride where you have a vertical cylinder, okay, and it's of course you have a floor on the bottom. So the person enters into this cylinder, and then it starts rotating. Now, when it comes up to a given value of the speed, when it's rotating fast enough, actually the floors on the bottom just drops away, and the person keeps kind of glued to the wall of the cylinder, so that both the person and the cylinder, they rotate together. Okay. Now the question is, given that the coefficient of static friction between the person and the wall is μs, and the radius of the cylinder is r, what would be the maximum period t, such that the person is not falling away, just like the floor. So the person will be kind of stick to the wall. So to do so first of all, we have to know what is the unknown that we are looking for. So we are looking for the unknown, which is the period t. And in this case, so the only way to access the period is by having the expression of v, because we know that v is equal to 2 pi r over t. And in such problem, the only way to access v, so to have an expression where v is present, is to access the radial acceleration, because the radial acceleration is given by v squared over r, where r is the radius of the circle along which the object is moving. Okay. Now we have to look, what is our object here of study? We have to study the person itself, because we want this person to be stick to the wall and not falling away. Okay, so we have to see how this object is moving, which is the person inside the cylinder. Now, whenever the cylinder is rotating around in a vertical plane, as you can see in here, if you take the person is actually moving along a circular path in this way. So it's just a circle. Okay, here is the circle. And what are the forces acting on this object? They are the following. So we are taking the person in a situation where there is no floor on top. So this is on bottom. This floor on the bottom, it has just dropped away. It falls, and then the person, it remains glued to the wall. So what are the forces acting on this person? They are the following. So first of all, you have the gravitational force. The gravitational force is the force exerted, again, it's downwards, the force exerted by the earth on the person. It's given by m times g, where m is the mass of the person and g is the gravitational acceleration. Then, since the person is actually sitting or just it's held to the wall, then we know that there is a normal force which is applied by the surface of the cylinder or the wall itself on the person, and this force is actually perpendicular to the surface of contact between the person and the wall, which means that this normal force, which is n, is along the centripetal direction, because it points towards the center of the circle. Okay, and then you should have another force that actually keep the person stick to the wall and avoid the person to fall away. So what is this force? Actually, this force is nothing else than the friction. So there should be a friction between the person and the wall, and this friction should be of static nature, because we don't want the person to move up or down. We want the person to remain glued to the wall. So this static friction should in fact opposite the gravitational force should be in opposite direction. So it should be upward, and it should be of static nature. So it should goes with Fs. Okay. Now, if I just take another figure where the person is just sitting on the side. So if you take the same, that this is the cylinder, okay, you don't have anything on the bottom, the floor has dropped away, and this is the person which is over here. So I'll just take this position because it's very easy to see the forces on this direction, on this position. So you have, as we said, the gravitational force, mg, okay? There should be a force which opposes this force such that the person remains in its position and remains glued to the wall, which, as we have said, it should be friction force of static nature because we don't want the person to be moving. And the wall exerts on the person a normal force, so it's perpendicular to the surface of contact between the person and the wall. And so this is nothing else than the normal force. Okay, so it's just another position of the person where it's clearly you could see how mg, fs, and they are drawn. And as we have said earlier, so the person is moving along a circular path. So here is the circle along which the person is moving, right? And here is the acceleration AR, which we know that the person is having because he is undergoing a circular path. So this is AR, okay? Now, as we have said, if we want to get the period, we want to get an equation where V is involved. And we know that V is, but it's in the definition of AR. So AR we can access through Newton's second law. Let's now apply Newton's second law on the person, make the projections, and then see what we get. So Newton's second law on the person, it's given by mg plus fs plus n equals ma, where a is the total acceleration of the person. Okay. Now, if we make so we have to take a choice for two axes. So let's take, of course, by default, centripetal direction to be the x-axis because it's on this axis that we have the acceleration. So this is the first motion. And then we will take this direction to be the y direction, so the vertical axis to be the y direction, which is perpendicular to x. And now what we will do is that we'll take the projection of this Newton's second law onto the x and y axis. So let's start with the x axis, for example. Just on the x axis we have, in this case, the only force that acts on the person is the normal n. So we can write down n equals to the mass multiplied by AR, where AR is the radial component of the acceleration. That's it. We don't have anything else. And along the y-axis, we have Fs plus Fs minus mg is equal to 0. So don't forget that we want the person to be stick to the wall. So we don't want the person to be moving, neither up nor down. So this is why we have a 0 on the right-hand side of the equation. And that's it. So we end up with Fs equals to m times g, right? Okay. Now, the point is we have to find an equation, okay, which gives us a condition on T, okay? What do we know about this static friction? So we know that the person, we want the person to be stick to the wall, so there should be a static friction between the person and the wall. But we know from the lectures that the static friction is able to grow. So we don't want the static friction to be above a given value, because above a given value, the static friction won't be able to resist to the tendency of the person to move, and therefore the person will move. So this is why we want Fs to be smaller or equal than Fs max. So it could be at maximum equal to Fs max. And we know that the value of Fs max is equal to mu s times n. So we want this Fs to be smaller than mu s times n, right? And we know what is the value of n. So we know that n is equal to from the first equation, it's equal to MAR over, so it's just equal to MAR, sorry. So we end up with mu S times M times AR is equal to V squared over R. But we know what is V in terms of T. So we know that we can write down V as equal to 2 pi R over T. So from here, we can write down mu S times M times V squared is 4 pi squared R squared. So what is the radius of the circle? The radius of the circle along which the person is moving is the same as the radius of the cylinder. So it's R squared divided by R. Pardon, divided by T, sorry. This is the period. Divided by T. Okay, let's say you see it, but divided by T. Multiplied by 1 over R, which was in the equation already, okay? That's it, so 1 over R. And on the other side, we know that Fs is equal to m times g. So we found an equation where we have a condition on the period t. So we end up with mg should be less or equal to mu s times m times 4 pi squared r squared over t times 1 over r. And now all what we need to do is just to cancel out the terms. So we have m and m on both sides. We have r here squared and we have r. And so we end up with g is smaller, or let me just go from here. So we end up with g smaller or equal to 4, so 4 pi squared r times mu s over t. Yeah, that's it. But we just have a factor here, which is t squared, so this is missing. It's over t squared. So this is the condition that we get on the t squared, and so we end up with t squared should be smaller or equal to 4 pi squared times r times mu s divided by g. And so from here we can deduce that t should be smaller or equal to 4 pi squared r mu s divided by g, where we have taken the square root because we have we had t squared before. So that's it. This is the condition on t. And so from here we can deduce that the maximum value of the period that it could take is equal to square root of 4 pi squared r times mu s divided by g. And therefore we have shown the first part of the equation of this problem. We have solved it. Now the second part, you just have to make a numerical application. So for the numerical application, you have everything in hand. You have the expression of Tmax. All what you need to do is just to replace mu s by 0.4, and r you have to replace it by I think 4 meters. And so you end up with the value 2.54 seconds. Now the continuation of this question was, how many revolutions per minute does the cylinder make? So to know this, you just have the number of revolutions per minute is that you have to see how much time does it take one revolution, and then see how much time you have, which is 1 minute. So the number of revolution, the one revolution, it takes 2.54 seconds. And 1 minute is nothing else than 60 seconds. So you end up with 23.6 revolution per minute. Or you can just apply this rule, which is given by, so if one revolution, it takes this amount of time, then in 60 seconds, how many revolution can you do? And then you end up with the same result.